Welcome all to another session on line commutated and PWM rectifier course. And today we will discuss about multi-pulse rectifiers. So if we see the total course structure, we are in week 2 and we are going to primarily look into this aspect today, 6 pulse and 12 pulse rectifiers and different types of transformer configuration, and also the input current analysis. Okay, we have already covered the THD and power quality issues in the previous lecture, and we are going to focus more on one of the solutions today to improve the power quality issue. So the solution that we are going to talk about today is basically this one, multi-pulse rectifiers. Okay, and this is a cheap solution, and it consists of basically transformer and usually diode rectifiers, although active front end is possible, but usually it consists of transformer and rectifier arrangement. But here the improvement in the input current, the harmonic improvement in the input current is done through some special transformer arrangement. The reason why we are studying this is because as part of this rectifier thing, as I told you repeatedly, one must remember the input side also, input power quality also. And this solution based on multi-pulse rectifiers is one of the most economical solution. It's a cheap and easy to fabricate, and it is and this technology based on rectifier and transformer is a very well established technology. And that is why in many of these applications, industrial drives, for example, we repeatedly see the use of such kind of multi-pulse high power converters or high power rectifiers. Okay, where these industrial drives have an input AC. So we'll talk about it. Let us go ahead. So many converters. So let us see what is this. We have seen this 6 pulse rectifier. So many converters require a DC at the input, right? For example, not only these motor drives need an DC. Suppose, how does the motor drive, induction motor or synchronous motor drives operate? From the grid. So there is a grid. So for example, let me draw it. So this is the grid. Okay, and then you generally have a transformer, right? And then we have a rectifier here. Okay, and after the rectifier it forms the DC link. Okay, and after this we generally have the inverter. Okay, generally this is the inverter, this is the rectifier, and then we can have a motor drive here, for example an induction motor drive, right? We can optionally also have filters at various places. For example, we can have an output filter here. Okay, output filter. This output filter basically improves the output of this inverter. Inverter output is the PWM switched waveforms, and we try to kind of like make it a little bit sinusoidal, and we also try to control the rise time and all those. So we use an output filter, but many times we also use an input filter. Okay, here input filter to improve the current which is being drawn. Okay, so often this is also used. So this is a typical arrangement of an industrial drive. And 6 pulse rectifiers have been a very popular choice for this. So this rectifier very often is a 6 pulse rectifier. 6 pulse rectifier means a 3-phase diode bridge rectifier. Usually it may be a thyristor based rectifier, but thyristor rectifiers are now getting obsolete. Okay, so generally we use the diodes here. Okay, so this is a 6 pulse rectifier, and it is available for a wide range of voltages and power. Okay, so it is a very popular choice. And if you see the output voltage profile of this converter, so we have here drawn the diagram of this 6 pulse rectifier. Here you can see, here is the grid, then you have this transformer, and then you have the rectifier, 6 pulse rectifier or the bridge rectifier, and then I have used a constant current load so as to emulate kind of a motor load, heavy inductor at the output. But the analysis which I am going to present today is equally valid if you have a capacitive load also. For example, in place of this one, we can also have a capacitive load with an equivalent load resistance. It is also possible. Okay, now how is the output voltage waveform? How does it look like? Typically, as you know, this consists of this 6 pulse rectifier output. So which means that we have 6 lobes here in one cycle. Okay, so here is this one cycle which I have drawn, and there are basically 6 lobes in the output voltage. So we can find out how much is the peak to peak ripple in this output voltage, because this is the function of the rectifier. Rectifier convert the AC into DC, and so we are getting a DC, but we have a ripple. Okay, and how much is that ripple? The ripple is basically, so if you take this as 1 here, and so this angle you can see, because there are 6 pulses, so this angle is basically 60 degree, right? 360 by 6. And so therefore this angle here is basically equal to 30 degree. And so therefore if this, and this is part of the cosine wave or sinusoidal waveform, so this is the peak of the AC waveform, and the nature of this waveform is sinusoidal. So which means that if I take this as this point is 1, this point here will be of course equal to cos 30 degree, which is 0.866, right? So which means, so this is what we have written here, 0.866, and so we say that the peak to peak ripple is almost like about 14% in this case, right? Output voltage. So this is one side. Okay, so this is where this is the output. So if we look into the output of the rectifier, which is available here, okay, this is the V0 output. What about the input? This is where the problem starts. Okay, the input current, as we have covered in some of the previous lectures, is that this input current, right, IA, this current here is a quasi square waveform, and this is going to be a problem which we know, and it leads to poor power quality at the input, like input current harmonics, and some standards like IEEE 519, it will not allow you to use this equipment in your factory or in the real setup, because it is violating this standard and you are drawing or injecting too much of harmonics into the grid. So this standard says that the total harmonic distortion, THD, okay, so the THD should be less than 5%. This is one of the standards which we said. Okay, so now then what is the solution that we are proposing now? The solution is to use, one of the solution is to use a multi-pulse rectifier. We will see other solutions as we progress on the course, right? We will see if I use a voltage source converter at the front, it can also improve the power quality issue. Okay, but you can also use other single phase. For single phase, we can use like totem pole PFC and all others, which we will see one by one, the input side. But one of the solutions that we will see now is like a multi-pulse rectifier. Okay, so what is the main advantage of multi-pulse rectifier? Number one is that it improves the input current harmonic distortion, so which means that the THD will go down. Okay, so that is one of the advantage on the input side. But it has also another advantage, and this advantage is that the output DC voltage ripple of the rectifier gets reduced, right? and so which means that the output voltage is now getting closer and closer to the DC, okay, pure DC. Okay, this is what we expect, right? Ultimately this is a rectifier. We want to convert AC to DC, and the better is the DC, the better is the output, right? So the ripple, if the ripple on the DC goes down, we just saw that the ripple with a 6 pulse rectifier is 14%. If we get it much lesser than this, it is beneficial for us. And at the same time, so there are two benefits happening. One is on the rectifiers, one is on the output side where the ripple is going down, and the other one is also on the input side where the input current also distortion is minimized. I would also like you to look into some of this product brochure of some of the companies. For example, this is coming from the company Danfoss, and there is some link which I have given from Siemens. So these product brochures, or if you search in the internet, you will see many literatures available from these companies. And what do they say? You can find out, you can see, for example, Danfoss is an electric drive company, so they make motor drives, and typically in their applications they use at say medium voltage or high, medium power levels, they typically use this kind of rectifier and inverter arrangement. The rectifier is generally 12 pulse rectifier, which we are going to talk about. So 12 pulse rectifier with a neutral point clamp converter, which is very common in use, right? So Danfoss uses this. Similarly, Siemens has these what is commercially called as the perfect harmony, and this Cinemix perfect harmony, and this has like extended delta connection at the input, and it has kind of like cascaded edge bridge structure at the output for medium voltage applications. So I would request you to go through some of these product brochures and also search in the internet where you will get a lot of information on how these kind of multi-pulse rectifiers are commercially used. They are very much used in real life. Now let us see the star delta 12 pulse transformer. Okay, so this is the first or this is the solution that we are going to study in details today. So what is there in a 12 pulse transformer? As we see here, there is one primary, okay, which is connected in star here, and there are two secondaries of a transformer. One is in star and another one is in delta, right? So there is a star delta transformer at the secondary. These are connected to the two diode bridge rectifiers, and then their outputs, this is the output, are series connected, okay. And then this output is kind of like fed into the load here. Fine. Now one of the things that you should note is that there is a particular turns ratio of these transformers. If you can see here, N1 is equal to 1 and N2 equal to 1. So which means N1 is to N2 is 1 is to 1, okay, for the star connected arrangement. However, N3 is equal to root 3. So the turns ratio between the primary and the delta is 1 is to root 3, right? And so this is something which we must keep in mind when this thing is going to operate. Now, each rectifier is going to produce a 6 pulse or 6 lobe wave. So for example, if you see the output of, say, this is suppose the V01 and this is V02, you will see that this V01 is something like this, okay. This waveform is which we just saw few slides back, that the output of the one rectifier is a 6 pulse waveform, right? Now the output of the second rectifier, so suppose this is V01 here, right? This is V01 and this is V02. So we can say that this is basically V01. So instead of writing V0, we can write V01 here, correct? So this is the output of the first rectifier, which is connected in star. Now what is the output or what is the waveform of V02? Here we have to be a little bit, you have to understand that this delta, the delta winding on the one of the secondaries causes a phase shift between the line voltages, right? So which means that if we observe the line voltages on the primary side and the line voltages on this here, okay, right, then they are in phase. However, the line voltage of the delta, so these 2 points, if we look into carefully, then there is a phase shift, because we know the delta winding causes a phase shift between the primary and the secondary here in this delta transformer. So this waveform, this line voltage will either have a plus 30 degree or minus 30 degree phase shift, okay, at the line voltages there, correct? Because there is a 30 degree phase shift between the star and delta, and that is why we often use this kind of arrangement, YD1 or YD11. Okay, those who know about transformer connections, they know that there is a phase shift between the primary and the secondary of 30 degree here. So therefore, if we now plot V02 on this waveform, what will we see? So let us plot that. So since so this is 30 degrees, so this is 60 degrees, so which means, right, so this waveform of V02, we are going to plot V02 will be something like this. Note that this is 30 degree phase shifted from the first one. Okay, so both the waveforms are identical. The blue one, so this is V02, right? Both the waveforms are identical. However, there is a 30 degree phase shift between V01 and V02, correct? Because of the delta connected transformer, which causes the phase shift. So when these, so we have now, you can see here, we have now added V01 and V02, and therefore the total V0 that comes up is the summation of these two waveforms, and I can now draw the two waveforms here, and this value, if you just go on adding, so this we are going to add the two waveforms, and it will be something like this. You will see that this waveform is like this, right? So basically you will see that there are now, this you can do yourself, you can do the verification yourself, right? And okay, so it is a sum of these two, and this will contain 12 lobes or pulses. Okay, so when we add them, so we get a 12 pulse rectifier. Okay, when you add one by one each of these waveform, you get a 12 pulse waveform. Okay, so the output, this is the V0 waveform, right? V0 waveform is a 12 pulse waveform, right? And this is what the output voltage looks like. And if you see it carefully now, that because there are 12 pulses which is spanning over a 360 degree, so the width of each of these lobes will be equal to 360 degree by 12, which is 30 degree. So which means that if this point is 1, this point here will be cos 15 degree, and cos 15 degree is roughly equal to 0.96, right? This is what is written here. Okay, cos pi by 12 and 0.96, and so therefore the peak to peak ripple here is now about roughly approximately 4%. Okay, so we see that the output voltage of 12 pulse rectifier is definitely much better than that of a 6 pulse rectifier. In 6 pulse rectifier, the ripple was about 14%, and in 12 pulse rectifier, the ripple went down to about 4%. Okay, so definitely we are making a better quality of rectifier when we use this kind of a transformer arrangement. But there is an additional benefit, okay, and that benefit comes from the input current, which means that this current is actually will get better when we use a 12 pulse transformer, and that is what we are going to see now, how the IA current actually is getting better. So in order to understand this, there is a little bit of analysis involved on how to draw or how to know what is the current IA. Okay. Now, in order to understand this current, we have to use some of the basic principles of transformers and the MMF balance in a transformer. So you can see here, this current IA, right, is basically equal to the reflected secondaries currents, right? So there is this primary and then there are two secondary currents. Now, so because this, if we first see the star connection, star secondary, this is the star connection and this is from the delta. This term is coming from the delta. Okay, so I capital A is nothing but, because we have an N1 and N2 equal to 1:1, so I capital A is IAS as coming directly from the star. Okay, N1 I1 is equal to N2 I2 MMF balance, and so therefore I capital A is equal to I small as. And what about the delta contribution? So this delta, okay, so this current here, okay, will have an MMF balance with this IA current, there IA dash, right? But now you have √3 factor that will come into the picture, because this current is this turns ratio is √3, right? So therefore N1 I1 is equal to N2 I2, so N3 IA dash, right? N3 IA dash N3 IA dash will be equal to N1 IA, and therefore when you reflect this current, right, so therefore will be equal to N3 by N1 into IA dash will get reflected, so IA reflected, and that is what I have written here. This is coming here, okay, N3 by N1 times IA dash, right, which is √3. So therefore if I, so the total current I capital A is IAS plus √3 times IA dash. Similarly, from symmetry we can also say IB and IC are exactly similar to it, right? Now let us see what is this current, this IAD current. Okay, let us find out this current. Okay, now by applying KCL here at this point, so let me rub this thing. So if I apply KCL at this point, we can immediately see that IAD, this current, is sum of IA dash and minus of IC dash, right? Similarly, IBD and ICD are similarly. So we do a little bit of mathematical manipulation, and we subtract 2 from 1. Sorry. And we subtract 2 from 1 here, and so we get IAD minus IBD as this value here. Now we can assume that this is a balanced three-phase system, so IA dash plus IB dash plus IC dash is equal to 0. Okay, so we can assume this condition to be true. Most of the time this is true. This is not true in case of an unbalanced system, right? So IA dash plus IB dash plus IC dash is equal to 0, right? And this is the internal current of the delta. And so substituting 5 into 4, what we get is that IA dash, this current IA dash we are trying to find out is IAD minus IBD divided by 3. Okay, so basically we are expressing the these currents IA dash with respect to the delta output currents. Okay, that is what we tried to express here. So we get IA dash, IB dash and IC dash. So these are the currents which are flowing. Now after we have obtained these expressions of the currents, we can say that the input current of the transformer is I capital A is IAS plus √3 IA dash, where we have already got these values of the current IA dash, IB dash and IC dash. Now what we will do now here is to plot these currents, right? We will plot these currents and see what is the IA waveform. This is what we are trying to get into. Okay, we are trying to get this input current waveform. We are trying to plot this current and see its property, right? So at first we are going to plot this IAS current, and you can see IAS is a quasi-square current, right? We know the diode bridge rectifier, the input current is a quasi-square. Next we plot the IAD, this current here, IAD. This is also a quasi-square current. However, this current is 30-degree lagging, right? Because of the delta connection, right? So IAS and IAD are identical, but they are phase shifted by 30-degree. Since IAD we have drawn, we can also draw IBD, because IAD and IBD will be 120-degree, IB will be 120-degree phase shifted. Okay, so this is 30-degree phase shift, and then we have the 120-degree phase shift, right? And so we'll be able to draw IBD, which is 120-degree phase shifted. Now we have already found out what is the expression of IA dash. IA dash is IAD minus IBD divided by 3. So we have got IAD, we have got IBD, and we will divide by 3, and therefore we will be able to now draw IA dash waveform. And you can see here the waveform of IA dash, and you have to also see the amplitudes here. You have to be careful about these amplitudes. Okay, it has a DC component which is 0, but the amplitudes we have to be careful. Okay, this you can just do it yourself also by hand, and you will get these amplitudes. Okay, the different levels of the waveforms. Okay, the levels. Now once we have got IA dash, right, so we can plug in into this equation here. Okay, so we plug in IA dash here, and we have got IAS here. We plug in these two values into this equation, and therefore we will be obtaining I capital A. And when you do this exercise, you get this I capital A waveform, which is shown here. Okay, and also note the magnitudes of these different levels. Okay, these magnitudes are important. Okay, now this is the waveform for the 12 pulse rectified input. So this waveform is actually completely different from this IAS waveform. Okay, so you can understand that because of this 12 pulse arrangement, okay, the waveform, input current waveform has completely changed. If there was no 12 pulse, so suppose if we had only a 6 pulse rectifier, right? So suppose we didn't have this thing at all, right? We had only 6 pulse, then this was the input current in that case, right? And this was very rich in harmonics. Okay, it has all the odd harmonics, 1, 3, 5, 7. It was very rich in harmonics. But now with this 12 pulse arrangement, now we have got this one. So our input current is actually completely changed. We have now this as the input current. Okay, now the waveform has completely changed, and then therefore we will now analyze what is the harmonic content, or what are the different magnitudes of harmonics, which are the harmonics present, which is the harmonic content of this waveform here. Okay, let us do this. In order to do this one, what we will do here is that we will split this into 3 parts, right? And we will then add the 3 parts. So here you can see how I have split the waveform. Okay, so this is here is the blue part. Okay, so basically we are splitting it into this part. So this is one part here, okay, this part and this part here. Okay, and this is basically a square wave. Okay, and this can be drawn directly here. Okay, so this is one part. Now note the amplitude. This amplitude this is ID by root 3, and I have drawn it ID by root 3 here. Okay, so this is the base part of the waveform. Next we have the YOLO part, right? So we have this YOLO part here, this YOLO part, and this YOLO part. We will take it out, and then we can draw these YOLO parts here. Okay, And note again the amplitudes. See here, this is ID. You have to be careful. Here is the ID waveform, right? So because this you see here, this is 1 plus 1 by root 3 and 1 by root 3. So this amplitude here, this amplitude is 1, right? This amplitude is 1 here. Okay, so this is how this ID waveform is drawn here. And then we have the last part, which is this one, the green part here and here, and this we take out and put it here. Okay, and then we will add the harmonic content. So let us see what are the harmonic contents. We have to recall what we had done with Fourier analysis a few lectures, Fourier series analysis a few lectures back. So what did we know? We found out that in a square wave, okay, the harmonic, the magnitude of the harmonics can be given by this expression 4id by root 3 n pi sine n omega t. This you can, we have derived it previously. So this is the amplitude. So basically 4 into I by n pi and sine n omega t. In this case, this I is equal to id by root 3, and that is how we got this expression here. Okay, so this basically this square wave has all the odd harmonics. Okay, 4id by root 3 n pi sine n omega t, right? Now what about the second waveform? What are the magnitudes of the harmonics? The second waveform, again, because of the symmetry, odd symmetry and all, it will also have only the odd harmonics, right? 1, 3, 5, all these things. And so this expression will be 4id by n pi and cos n pi by 6 and sine n omega t. Okay, so this is the expression for this one. So here this n pi by 6, cos n pi by 6 is coming because the break in this waveform occurs, or the discontinuity occurs at pi by 6. Similarly, this is another quasi-square waveform and the break happens at pi by 3. So therefore 4id by root 3 n pi like this, and then cos n pi by 3 here. Okay, this you can just verify. So these are the magnitudes of the harmonics which are present in the different parts of this waveform. Okay, so these are the three parts, and 1, 2 and 3, which are parts of this waveform. And so we can then, the total harmonic content is f1t plus f2t plus f3t, and will be something like this. Okay, so therefore now let us put the values. Put n equal to 1. Okay, if I put n equal to 1, and in this expression we get ft equal to 4 root 3 id by pi into sine omega t, right? This we will directly get. Now if you put n equal to 5, okay, what will you get? So you will get 1 by root 3 plus cos, okay, 5 pi by 6 plus 1 by root 3 cos 5 pi by 3. So what is the value here? So 1 by root 3 Okay, so here you can see that when you put these values here, this value will come out to be, if you put n equal to 5, the value will come out to be 0, right? So this, when you put n equal to, so for the fifth harmonic, the magnitude is equal to 0. Similarly, if you put n equal to 7, again you will see that you can just put n equal to 7 in that, and you will see that ft is equal to 0. But this is not true for n equal to 11. Okay, if you put n equal to 11, you get a value, and that value is equal to this one, okay, sine 11 omega t. Note that the magnitude of the 11th harmonic is 1 by 11. So this is 1 by 11th of the fundamental. Okay, this is important, right? So what we are getting with this 12 pulse transformer is that we are eliminating the 5th and 7th harmonics. That is first thing that we are able to see. But the next harmonic, which is coming at 11, has an amplitude which is only 1 by 11 times that of the fundamental. Okay, this is very important. So we have eliminated some harmonics, and the amplitude of the 11th harmonic is also very low. Okay, so therefore we can say that the 12 pulse rectifier substantially reduces the harmonics in the input current. Okay, so harmonics present in input current at 11, 13, 23, 25, and in general 12n plus minus 1 harmonics are present. Okay, so 5th, 7th, 17, 19, these harmonics are all gone. Okay, and you should also note that the harmonic cancellation in the input current occurs due to the corresponding harmonic flux in the transformer core. Okay, so basically the cancellation of harmonics is happening in the transformer core only, because that is where all these currents and the corresponding fluxes are getting added up, and some of these fluxes, the harmonic fluxes, are cancelling each other, and that is why the input current does not contain these harmonics in this. Okay, so therefore we can say that the 12 pulse rectifier has an input current which is 11, 13, 23, 25. In general 12n plus minus harmonics will be present at the input side. Okay, and there is one simulation here which you can see here, which is very similar to what the waveforms show. So IAS and IAD has been shown here, and these actually contains the 5th and 7th harmonics here, you can see. But when you go to I capital A, right, you can see that this is the fundamental, but then this 5th and 7th, these harmonics are totally gone, and we have 11th and 13th harmonic present in the input current, total input current. Okay, now so this concludes what is a 12 pulse transformer. In many cases we actually try to improve the harmonics further. So with a 12 pulse transformer, often with a low value of inductance, we may not be able to always kind of like maintain the THD less than 5%. Sometimes the THD can go more than 5%, 7-8% it can go, 12 pulse transformer. So we will be able to use even higher pulse rectifiers. Okay, so this is a little bit advanced, and in that case, so suppose we use 18 pulse rectifier, 24 pulse rectifier, 48 pulse transformer rectifier. So this is not transformer plus rectifier arrangement. Okay, and this is a little bit an advanced slightly, so we take it up at a postgraduate level. Okay, so we were not going to cover this one. Actually, this has been covered in one of my other lectures, high power converters, which is also available in NPTEL YouTube, and you can get it in NPTEL YouTube, right, where we have talked in detail about this multi-pulse transformer. Okay, you can go through it, but basically these kind of higher pulses are used in high performance drives, or it is in many cases used in high voltage DC transmission, HVDC transmission, okay, from where these concepts have come. So there we use zigzag transformer or an extended delta transformer. Okay, so I'll just show you one of this kind of like very high performance drive, okay, which is made up of like cascaded edge bridge. But what is important here is this is the zigzag transformer arrangement, zigzag transformer with a rectifier arrangement. Okay, what it's done here is a zigzag transformer can produce a particular phase shift as desired by the user, phase shift between the input line voltage and the output line voltage. So if you see here, this zigzag transformer, there is this input line voltage here, and then there is an output line voltage. Okay, and this angle here indicates that there is a phase shift between the line voltages of the input and the output. So this is the input and this is the output, and the phase shift between these two line voltages is minus 24 degree, which means the output is like lagging the input voltage by minus 24 degree. And this is done by kind of like cutting the winding of a conventional transformer and rewinding it in a different fashion. This is covered in that other course where I have talked about it in details. I'm not going to talk about it in detail, but here you can see that you can have other types of phase shift like minus 12 degree, 0 degree, plus 12 degree, plus 24 degree. So you can have actually the output voltage shifted with respect to input. Okay, this not only improves the output voltage quality, but it substantially improves the input current quality as well. Okay, so this improves a lot. So this improves a lot. Okay, and the input current become like very close to sine wave. Okay, and you are well within the IEEE standards and like this. Okay, so this way if we look at it, okay, this is another solution. There is also something called as extended delta connection, which again we can see here in the other lecture, extended delta, which is also used to kind of like improve on the profile of the input current. Okay, so with this we conclude the thing of multipulse transformer, and and this is one of the easy to understand and easy to fabricate, cheap. It's a very cheap solution because you just have to use a transformer and some rectifier arrangement, and also this is kind of like a very robust solution. Okay, transformers have been here for more than 100 years, and rectifiers are also very robust thing, very robust power electronic component. And so therefore this solution is also very popular not only in drives, but also suppose if we build EV charging. Okay, suppose we want to make large scale megawatt level charging infrastructure where we want to charge batteries. Okay, so we have to it's not a residential battery charging, it is a like a commercial large scale battery charging, which is going to become popular very soon. Okay, for example, in India, if we adopt more and more electric vehicles, it is not possible for us to kind of like charge in our houses. Suppose we are adopting large scale a fleet of buses where this needs to be charged simultaneously from the grid, and this needs to be charged fast also. We cannot keep on charging for very long duration, 12 hours, 16 hours, we cannot charge. We have to kind of like charge it very quickly also. So in that case, we need this kind of rectifiers. And one of the solutions that is possible is like based on multi-pulse transformer with a rectifier arrangement. Okay, and this is something which is very much economical and ready to use, although it has its own drawbacks. One of the drawbacks is that the size of this transformer is quite big. Okay, this kind of multi-pulse transformer has one drawback, is that these are all 50 hertz transformers, and so the size of this transformer is very big. Okay, and so people have actually thought of something else which is also called a smart transformer. Okay, which will not we will not cover it in this course, but smart transformers are power electronic based transformers where we actually do this isolation. Here the isolation is done using a 50 hertz transformer, but in a power electronic transformer or a smart transformer, we convert this AC into a DC at first, and then we have a high frequency DC-DC converter or a high frequency DC-DC conversion. Okay, and then when we go for the high frequency DC-DC conversion, the size of the transformer becomes substantially smaller, very small size. We may be like 10% of the size of this kind of a transformer for the same power rating. So the transformer size becomes much smaller. But the problem with that approach is, again, it's number one, much more costly than this, and it's a much more elaborate solution. This is a very simple solution. Okay, and so because you are going to high frequency, you are first converting AC to DC, then you are going for high frequency, you are using a lot of power electronic devices, switching them. So this is something which one must weigh, or which one must consider which solution is to choose when we want to rectify. Okay, so anyway, we have covered one of the solutions here, and in the next class onwards we will start looking into other solutions like voltage source converters and what is their impact and how do we so basically we will start with the what is called as PWM rectifiers from the next class. Thank you.